So I wanted to start class by quickly doing an example of what I talked about at the end of class on Thursday. And then we will start into how to understand these mappings and linear transformations better in terms of their ranges and things like that. But first I wanted to do the composition of two geometrical transformations. So we want to have one geometrical transformation, and then we apply another geometrical transformation. So just the way you compose functions in calculus, you can compose geometrical transformations. So what I'm going to do is I'm going to compose the following two transformations. So first I will rotate counterclockwise by pi over 3. And then I will shear in the x2 direction. And I want to get the language quite right. In the direction minus x2 by the amount 2. So whatever we have here, first we're going to rotate it counterclockwise by pi over 3. And then, once we've rotated it, we're going to shear it. And so if I call this transformation T1, and this transformation is T2, I have T1 goes from R2 to R2, and that's the rotation. T2 goes from R2 to R2, and that's the shear. And if you compose them, then you're going to have a linear mapping from R2 to R2, which corresponds to first rotate and then shear. So I will do this the slow way and then the fast way. Okay, so the slow way is to first find the standard matrix for T1 and for T2. So what this means is that, translation, find A so that T1 of x is equal to A times x, B so that T2 of x is B times x. So A is going to be matrix and B is going to be a matrix. Then that tells me that T2 composed with T1 of x. So by definition, that is T2 of T1 of x. T1, to compute T1 of x, I just do A times x. So that's because A is the standard matrix for the linear mapping T1. And now I want to apply T2. So what T2 does is whatever you give it, it multiplies it by the matrix B. So this would be B times A times x. So this gives me B times A times x. So the first thing I'm going to do is I'm just going to find the matrix A and I'm going to find the matrix B, and then I'm going to multiply them. Okay, so to find the matrix A, I need to figure out what happens when I rotate. So to find the standard matrix, first you have to choose the standard basis, and then you have to figure out what happens to each vector in the standard basis. If you chose a different basis than the standard basis, then you would get a different matrix that represents the linear transformation. It'll still work, but it will look different because you've got a different basis. For this one, we're just talking about the vector 1, 0, which, as last time we discussed, is going to go to cos theta sine theta, where theta is equal to pi over 3. And then I figure out the second vector. That's going to go to that. And what are the coordinates of that vector? Well, this one is 0, 1. Perfect. And what does it get sent to? Minus sine theta cos theta. And what you're doing is you're using the fact that that's the angle theta and that's the angle theta. So by the calculations we did before, we know that this allows us to write down the matrix, which is cos sine minus sine cos. I'm being a little bit lazy there. Now I just need what is cosine of pi over 3 and sine of pi over 3. Cosine of pi over 3. What is cosine of pi over 3? Affectionately known as cosine of 60 degrees. 1/2. So 1/2, 1/2. And then what is sine? Root 3 over 2. All right. So that gave me the matrix A. Now to get the matrix B, I'm going to do the same thing, but I need to figure out how the things, I don't want to look at those vectors. I want to just, over here, figure out what I have. I have, if this is the square, that's 1, 1, 1, minus 1, minus 1, minus 1, and so forth. That's going to be sheared in the negative x2 direction by the amount 2. So in the negative x2 direction means I'm going like this. And by the amount 2, it tells me that this is going to go down 2. So that goes to this right here, goes to 1 minus 1. This right here goes to 1 minus 3. This here is going to go up to minus 1, 3. And this here is going to go up to minus 1, 1. And then I connect the dots. This and this, it doesn't look like it. This is the point 0, 1. This is also 0, 1. And this is 0, minus 1. That's 0, minus 1. Because this segment is not actually moving. Everything is shearing relative to it. Yes?
Why does it go in that direction, not the other one?
Other questions? Yes? Sorry, what, love?
The two right coordinates goes up.
That would be plus x2. So that's the positive x direction. That's the negative x direction. And so you're just imagining you're shearing this side down and that side up. At some point, you're just going to have to memorize it. This is shearing in the negative x direction. If I were to shear in the positive direction, I would end up with something that looked like that. So That's the positive x2 direction. This is the negative x2 direction. This is the positive x1 direction. This is the negative x1 direction. Other questions? Okay, so with all that said, to represent the matrix, we need to figure out where this vector goes and where that vector goes. So 0, 1 got sent to that. Sorry, that's 1, 0 got sent to that. And 0, 1 got sent to that. So we have that T2 of 1, 0 is 1 negative 2. And T2 of 0, 1 is 0, 1. So this tells me that B is what happens to 1, 0. That's 1 minus 2. 0, 1 gets sent to 0, 1. And so if I want T2 composed with T1 of x, that's going to be B times A times x. And I can multiply those two matrices out. 1, 0 minus 2, 1 times 1/2 root 3 over 2 minus root 3 over 2 1/2 times x. And so that gives me this times that is 1/2. This times that is minus root 3 over 2. This times that is minus 1 plus root 3 over 2. This times that is root 3 plus 1/2. Okay. Now, if I had wanted to shear first and then rotate, would I have gotten the same linear transformation? This is the standard matrix for the linear transformation, which is please rotate and then shear. If someone said, is it okay if you shear first and then rotate? To answer that question, what would you compute? You would compute A times B. And if by some miracle B times A equals A times B, then you would get that it doesn't matter which order you do it. If they're not equal, if B times A does not equal A times B, then it does matter which order you do it. So examples where it's obvious that it doesn't matter would be like rotate by pi over 4 and then rotate by pi over 3 versus rotate by pi over 3 and then rotate by pi over 4. So it's clear that rotation is going to have the A times B equals B times A. But for this one, I doubt it. Are there questions? Okay, so then the fast way of doing this would have been first figure out what this goes to, and then shear this to figure out what it goes to. Now figure out what this goes to, and then shear it to figure out what it goes to. So do you think you can do this on your own, or do you need help?
Yeah.
Need help. Okay. So that's all right. Help is good. So let's start. So this vector is going to get sheared downwards. So it's going to go downwards. And this vector is going to get sheared upwards. I'm going to give them their coordinates. So cosine of pi over 3 was 1/2. And sine of pi over 3 was root 3 over 2. Minus sine, this is minus root 3 over 2. And that's 1/2. Okay, for sure, when you shear this vector downward, what is the first coordinate going to be in the resulting vector? It's going to be the same. So for sure you know that first coordinate is 1/2. And when you shear this vector upward, what's the first coordinate going to be? Root 3 over 2, minus root 3 over 2. So now you've got half of your matrix figured out. And already you can see that the first row is going to work out, right? Because whatever happens to this vector is going to go into the first column. And whatever happens to this vector is going to go into the second column. And so you see already you've got the 1/2 and the minus root 3 over 2. Now you just have to figure out how much to shear up and down. And so this is where things get a little bit tricky, because if I ask you what happens to this line, or this line, or this line, we know that this line goes down by 2. But this middle line, does it go down by 2? No, it goes down by less. And the closer you are to the center, the less you go down. And so you have to figure out, if you are 1/2 out, how far do you go down? So that one is nice, especially if I could draw, so let's pretend I can. That's this one, and it has gone down by 1. So this 1/2 has gone down by 1. Does everyone see why this is? If you're 1 away, you go down by 2. 1, 1 went to 1 minus 1. So this thing went down by 2. If you're 0 away, you don't go down or up by anything. If you're 1/2 away, you're going to go down half as much. And so going down half between going down not at all and going down by 2 would be going down by 1. So this is going to go to root 3 over 2 minus 1. So now, uh-oh. Oh dear. Yes, it is. Sorry, I was fixating on this. Okay, so we're happy with this entry. We're happy with this entry. We're happy with this entry. We just need to get that one. So this one, so basically, the further out you are, or the further in you are, you take this and you multiply it by 2. So here, you were out by 1/2. This times 2 is 1. For here, you were out by 1. Multiply 1 by 2, and you go down by 2. Here, you're to the left by root 3 over 2. So you multiply root 3 over 2 by 2, and you're going to go up root 3. So this is going to go to root 3, hold on, 1/2 plus root 3. So now that I figured out that this vector goes to this vector, goes to that vector, I write down the first column of my matrix, 1/2 root 3 over 2 minus 1. This vector goes to that vector, goes to that vector. I get the second column, minus root 3 over 2, 1/2 plus root 3. That's the matrix that represents T2 composed with T1 of x. Yes?
Where did you get plus root 3?
Sorry, what?
The root 3?
Why did I get the plus root 3? So this has to do with how far away from the x2 axis I am. And the further away I am, the more I'm going to fall. So if you did a strip, so extend this to a strip, you'll see that the further away you are from what in high school you called the y-axis, the further down you have to go. And so to figure out how far down or up you have to go, you first figure out how far away am I, and then you multiply by 2, because this was shearing by the amount 2. So for this point, which was 1/2 to the right, I take 1/2, I multiply by 2. 1/2 times 2 is 1, and I drop down by 1. So that's what told me that 1/2 root 3 over 2 went to 1/2, and whatever this coordinate is, decrease it by 1. For this one, I'm root 3 over 2. I'm root 3 over 2 to the left. What's going to happen is this vector is going to keep its distance from the x2 axis, but it's going to go up. The question is, how far up does it go? That has to do with how far away it is. So it is root 3 over 2 away. Because I'm shearing by the amount 2, I take root 3 over 2 and I multiply by 2. So that gives me root 3. So this I lift by root 3. 1/2 plus root 3. So basically, if you just take this infinite strip and you shear it, because it's a linear transformation, you know that rectangles are going to go to parallelograms, and you know that the image of this has to be that, and that tells you that the further you are away from the shear center, the more you have to drop. If you just dropped by 2 the entire time, this thing would, I don't even want to try and draw it. If you just said shear everything by 2, then you would get that the image would be that. If you just said drop everything by 2 and raise everything on the left-hand side by 2, that would be this would get sent to that. And that's not linear, and it's not a shear. Questions? Okay, so given any problem of this type, you have to figure out whether you are personally more comfortable writing down two matrices and multiplying them, or whether you are more personally comfortable figuring out what happens to two vectors. Yes?
Is the method of multiplying two matrices ultimately significantly slower?
Well, it's certainly slower if they're 3 by 3 matrices. It's slower. Sometimes we write questions so that doing it the smart way gives you the answer in 1 minute, and doing it the safe way gives you the answer in 5 minutes. But ultimately, we time our exams so that if you do things in the safe way, you can complete the exam correctly in time. It's just if you like to do things the smart way. It saves you more time for other questions. Are there other questions? And I should emphasize that one advantage of doing it with this matrix way is that you can actually ask the question immediately of whether it matters which order you do things in. If you had asked the person who did it the let's track the vectors way, whether it made a difference which order you did things in, they would have to actually go back to the beginning and first shear and then rotate. Whereas someone who did it this way could just say, oh, I'll just multiply the matrices in a different order, and now I've got my answer. So depending on what the question is, sometimes the approach can be different.